Hello everybody, here's your first homework video in terms of water in the atmosphere, our next unit. Water is obviously a very important piece to us in meteorology because when we go outside or we're getting ready to go somewhere, we want to know, is it going to rain, is it going to snow? We might want to know if it's humid or not. So this is a very important piece to meteorology, obviously. So it really starts off with the hydrologic cycle, or as we might also talk about, is the water cycle. Please don't mind my bad handwriting, right? But this is what it really references. So water is a really unique substance because on Earth it can exist as a solid, liquid, or gas. Try to find another substance that can do that at normal temperatures that we experience here on the Earth's surface, and you just won't find it. So the hydrologic cycle is the movement of water from different reservoirs, like places where that water is stored on the Earth. It could be in the atmosphere, it could be on the Earth's surface, it could be as groundwater, it could be frozen in glaciers. Anywhere where water would exist naturally is a part of the hydrologic cycle. So if we were to actually go ahead and look, you've probably seen tons of graphics. You've learned about these when you were kids, right? In many classes, the water cycle is that movement. And again, it could be as solid, liquid, or gas. All right, so we won't spend too much time here since it's not a new concept. But what we will talk about, which is really important, is heat and how heat is involved in the water cycle. So this graphic basically shows phase changes, all the changes of water from one form to another. All right. So the important piece is if I move from left to right in this direction, right, we know that we are absorbing energy. If we move in this direction on this graphic, we are releasing energy. So for example, if I were to have water on the Earth's surface and it evaporates, obviously we'd need to input some energy, probably solar radiation from the sun. Those water molecules are going to vibrate faster, they're going to escape the liquid and become a gas that exists in the atmosphere. So the only way for that liquid water can move on this specific direction on this graphic is if it absorbs energy, right? Now the opposite's true. If I want water vapor to turn into a liquid, right, since gases are hotter than liquids, right, that water vapor is going to have to release some energy. So that energy's got to go somewhere. So evaporation is a cooling process because the water removes heat from its surroundings, where condensation is a heating process. The water vapor has to release some heat outwards to its surroundings, probably the surrounding atmosphere or surface it's condensing on, in order for that water to turn from a vapor back to a liquid, right? And that's something we've talked about already called the latent heat. All right, so let's jump to the next slide here. All right, and just kind of summing it up, gases are warmer than solids. Gas molecules have more thermal energy than solid molecules. So evaporating water absorbs energy from the environment, and condensing water releases heat to the environment. So that's our latent heat concept that we've talked about last unit, and we'll continue to talk about it. Of course, you've probably seen this guy before, or someone like it, that is a little warm and you sweat. So think of a humid day. Well, geez, why is it that humid days are so dangerous? I don't know if anybody has been to Arizona, but people will talk about how it's 100 degrees, but it's much more comfortable than being in 80, 85 degree weather in Florida, for example. So the reason why we sweat is that we want to release some water, right? And once that water evaporates, it takes the heat away from your body to turn that water into a vapor, right? So if you have a hot, muggy day and the air is just kind of sitting there, that you're not going to have a lot of evaporation because there's already so much water in the air, right? So what do we do to help us facilitate evaporation? We get a fan, right? As that air moves across your skin, it helps pick up that water off your skin and helps facilitate the evaporation process as new air is constantly cycled in over your skin, and you feel cool, right? Because you're removing that heat energy from your body. All right, so when we talk about the atmosphere, we talk about it as a solvent, which is kind of a chemistry concept, right? And once water evaporates, it kind of dissolves, if you will, in the atmosphere. So the water vapor molecules are gases, and they exist evenly mixed in with the other gases in the atmosphere, like nitrogen and oxygen. Now, if there's too much water in the atmosphere, the water condenses and it precipitates out, and that's how we get clouds and rainfall. All right, so if you've ever had coffee, you know that if that coffee gets cold, that sugar, if you put any sugar in there, it'll precipitate out and fall out to the bottom. You get a layer of sugar on the bottom. Same kind of thing. Also, if you think about lemonade, if you make lemonade from the powdered mix, if you put too much in there, you'll get that sugar that precipitates out because the water can't hold any more of that sugar. Now, if you wanted that lemonade to hold more sugar, you could heat the lemonade up. Not that you'd want to drink warm lemonade, but you could get that additional sugar to evaporate, if you will, or redissolve and become a part of that solution. So water in the atmosphere works very much the same way. Okay? So we'll talk about humidity, all right? Something that you're familiar with. Now, the key with humidity is to remember that humidity can mean two different things. There's two kinds of humidity. Relative, which says, gee, how much water vapor is in the air compared to how much it can hold. So we can have the same relative humidity when it's hot and cold, but we'll have different amounts of actual water in the air, which we call absolute humidity, which actually measures the mass of that water. So if I were to take a box of water, of air, I would say, well, gee, how much water vapor is actually mixed in with that air? What's its weight? And that's the difference between absolute and relative. All right, so they can be very deceiving if you don't understand those differences between them. So, for example, a relative humidity of 90% on a cold winter day is very different than the relative humidity on a warm summer day if it were 90%. And you would know when you went outside, you would not be very comfortable. All right, so let's talk about saturated and unsaturated air. All right, so this basically refers to that relative humidity concept. The atmosphere is said to be saturated when it holds all the water vapor it can hold. Okay, warm air can hold more than water vapor than cold air. All right, within clouds, fog, and areas of precipitation, the atmosphere is said to be saturated. Right. So that relative humidity piece comes into play in helping us determine how close to saturation we are. All right. So we've talked about the Golden Gate Bridge and the fogs in San Francisco. There's a reason why we're studying it. This is just an environment where a lot of fog is natural. And fog is basically a cloud at the ground. So you need condensed droplets of water in the air to form fog or to form clouds. So saturated and unsaturated air is a big component about where clouds form and how they form. All right. We'll also talk about dew point. All right. Dew point is the temperature air must be lowered for saturation to occur. Right. Air is saturated if the dew point equals the temperature. I'm going to highlight this because this is really important. Right. And of course, you've experienced different dew points. Right. Here's a pick from a weather graphic. Right. You've probably recognized days from being in the summertime where the dew point was up in the 60s to maybe low 70s, and it's just not fun being outside for any extended period of time. I was in Florida last July where the dew points were in the mid 70s to upper 70s every day. Again, just not much fun. So that's telling you don't have to cool the air very much to reach saturation, so it tells you there's a whole lot of water in the air. So dew point kind of connects better with absolute humidity. Although it's not exactly the same thing, but there is definitely a connection to it. Okay? So calculating relative humidity, you require the dew point. And this is something we'll practice a little bit in class. Here's the equation. You take, and there's a chart that goes along with it. The one important piece is you are not dividing dew point by temperature. That does not give you relative humidity. A lot of students make that mistake. There's actually a special chart that we use to help us determine that piece. So we look at what is the vapor pressure from the dew point? So basically, what is the pressure the water vapor would be exerting divided by what the vapor pressure would be if the air was saturated at a temperature. All right, so we would use that chart, go ahead and make the calculation, and it would look something like this. All right, and again, I'm not going to spend too much time on this with the video because we'll practice this in class, so you'll see this. But I do, again, want to point out that the relative humidity is never dew point divided by the air temperature, because it'll just give you the wrong answer, and we'll learn about why that is. The last piece we'll talk about, another way to measure dew point, is what's called the wet bulb temperature. You use this tool pictured here called the sling psychrometer. Again, this is something else that we'll do in class, where you sling the thermometer around. You'll see, if you note down here, there is a little bulb here with a cotton wick on it that's wet, and then you sling it around, the water evaporates, it cools the bulb down, and the amount it cools will tell you how much water actually evaporated off the wick, and there's a way to measure relative humidity with that too. So that is something else that we will also practice. And that goes along with it is an actual chart. And again, I'm not going to spend too much time going over this because we'll practice this in class with some labs that we do, but I want you to see this and be aware of it. All right, well, that's it for this video. Hopefully this makes sense. Let me know if you got any questions, and we'll talk to you guys in class. Take it easy.